Hello, everybody. This is perfect timing. Everybody can come too early. This is an art to come on time. So it is my great honor and pleasure to introduce our second science professor, Elmar Wagner from Morelia, Mexico. And this will be a mini lecture course about compact quantum surfaces. The floor is yours, the film is yours. Take it away.
Oh, thank you. So, yeah, let me repeat the title. Compact. Not compact. Can you read it?
Yeah.
Compact quantum surface. That's the title of the lecture series. I need to get used to it. So this is time semester about graph algebra. So I would like to tell what has to do with graph algebra. So the idea is study something in much higher dimension. Study non-commutative CW complexes. And here comes the star as a classified algebra. This algebra does provide many interesting examples. So if we study classified algebras in the framework of non-commutative complexes, that's what I want to do. And it started all actually by Szymanski and Hong with Ali, and read all these quantum spaces as numerous CW complexes. Shortly afterwards, the community in Warsaw was faster and published it already. But that doesn't matter. So the idea is to what we want is, if you talk about non-commutative CW complexes, you have some idea what should be the topological space, and then you want to study the topological invariance. Logical invariance, and there's a path invariant in terms of k-groups. So it's hard because it doesn't classify. It classifies actually the closed quantum service, but it's usually not enough to classify manifolds. But it's easy to compute and it's easy to transfer from the classical case to this non-commutative style sheet path. So what was our aim with Ale is to find condition to get a comparison theorem. Under certain condition, we want to show or conclude that so K-group, the classical K-groups for in the non-commutative case is isomorphic to the K-groups in the classical case. Yes. So,
how these spaces are related? Whose K-groups you are comparing?
Yeah, that's actually so. Well,
To the formation of
no. The thing is, maybe you want to go by induction. Maybe that's why I explain it. Maybe so. The idea is to go by induction. What does it mean? And then I can tell you what I mean with in comparison during induction. So we have, if we know it for, let's say in xn minus 1 skeleton, commutative or non-commutative, and we can identify the K groups. Now, the cluing map, we have some sort of a cluing map. Let me call it whatever it is, P from, so we have these C and X n minus 1, Q complex, and then to clue some balls, we need to clue disks on the skeleton. So that we give something in some sum of C boundaries of balls. I like to call it like this. That's what, so these are n disks. This mapping is a cluing map.
Sorry, C stands for continuous functions, yes?
Yeah,
Complex values.
complex. Yeah, right.
And the Q means
Now
it's so on the left you have the non-commutative.
I can put it in Q here. Oh, still a razor.
Yeah.
It doesn't matter too much. So here you put Q's. Now the first thing is, of course, these disks and its boundary spheres should have the same K theory and its classical case. Otherwise, it doesn't make sense to call them disco boundaries. Now we suppose that we know this one, the K theory of the Q-deformed n minus 1 skeleton. We suppose that we know it's isomorphic to the classical case, and we can identify the generator. The generators do come from these cluing disks on skeletons. So if you can identify the generators, then we look at this map. Here we get K0 or K1, we get copies of Z. We can here as well identify the generators. So if this one was classically, well, if you have an isomorphism, let's look at it like this. So continuous functions, the classical case. Oh, I should put K, K groups. So now that becomes the induced maps. I should put here the K groups, which are then copies of Z. We suppose that we know that the K groups are isomorphic. And then we go, so we have some cluing maps here. That means we identify, actually it would go the other way around. These disks are clued to the skeleton. Then we get here the K groups of the classical disk, which are the same. This. And we want to have this one isomorphic and this diagram commutative. And then we want to conclude that we get in the higher skeleton isomorphic K groups.
Sorry, two questions. One question, okay, about this C of X. So in the lower part of this diagram, this really means continuous function. In the upper part, you work with something which is non-commutative. So this whole package is meant to be some non-commutative algebra.
Yeah.
The XQ just exists in some virtual sense. Yes. It's not a genuine set. Yes.
Yeah.
This is the first part. And the second, this isomorphism, identifying the classical with quantum, comes from some map, or it is just
one is part of the comparison theory, and that's why I start this compact quantum surfaces. You will do it by induction on M. On the dimension n, and the case. So the first step would be n equal to 2. That's already no commutative, and here everything works. So the result is everything works. And then you can see what I mean with this gluing, identifying. So it's so we have well, in this case, it's enough picture sequence. So you get pullback diagrams, you can even do myobiotories, but in the end, you can see that the generators of case theory all come from the disks, from the case theory of disks. So the even disk has the open even disk has K0 non-trivial of Z. The odd disks, open disk have K1 non-zero generator. We follow these generators. So how do we map? How does it go? How do we map the generators from the disk into the skeleton? And in this case, we just follow the 6-time exact sequence. We can compute case theory.
Okay, but this somehow addresses this horizontal part. But my question was about the vertical part. So
That's exactly what I mean. We need to keep track of of all generators. So these generators from the disks, some survive, some don't survive. If you lift them to the skeleton, and you have to keep track of the generators.
okay, maybe I'll put my question in
No, it's
different ways.
part of difficulty that you face.
So my question is whether this map, you have your diagram in K theory. My question is whether you have genuine maps on the level of algebras.
Here, no, only on groups.
Only on K theory. So this.
That's an isomorphism of abelian groups, and you hope that we can identify the generators. Where do the generators come from? Can we compare it? So we can say this generator comes from this open disk as defines a K0 element.
Okay, so this vertical isomorphism on the level of K groups does not come from the map between algebras.
No.
Okay, that's my point. Mm-hmm.
So now in the so quantum surfaces works very well. That's what I want to show you in this week's lectures. And if I have time, so the general case is use the Chauchet spectral sequence. So these complexes come with a natural filtration. And in the Chauchet spectral sequences, the entries of E1 page are just case theory of these disks, so are just Z copies of Z. And then we have to look at the D1, and what you observed was that D1 differential on E1 is exactly the same classical and quantum. And it's there where we can really identify the generators. You start with these generators, apply E1, map another generators, and say, well, that's classically and quantum is the same. So the spectral sequences, in fact, it's just how to assemble all the 6-time exact sequence. One can try computing 6 times exact sequence, higher dimension. There's another 6-time exact sequence, higher dimension. So the spectral sequence does assemble.
So your answer is almost yes for his question. Although you don't have a map induced geometric map, you are keep tracking generators of geometric origin.
Yes.
So this is something between the map induced by some geometric map and something completely in the category of abelian groups.
Here already you don't have a map from the quantum disk to a classical disk.
So but the generators,
but the generators we can identify. Number
you
1, 2,
construct somehow these generators.
Excuse me?
You have to construct this generator.
Exactly.
And the source of your generators is what?
all the generators is you will. I need to come to the spectral sequence. All the generators come really from the generators of disks, open disks.
So you,
Are the generators.
but you are assuming that you have K groups
Yeah.
together with some set of generators.
Yes.
Okay.
And then the problem is then you have differentials.
Okay.
So this is spectral.
So differential, so it's a part of structure, isn't it? So also differentials in a spectral sequence is a part of structure.
Yes, that's an important part.
Okay, okay.
That's a part that we have to compare, and that's a difficulty. So what happens in what we did is we have an explicit, I hope I can get to this point. If you're interested, I don't know, suppose they are students, so I shouldn't be so fast. If I get to this point, we can describe D1 generator. So we write down the first page, and the D1 can be compared. D1 in the classical case can be exactly compared with the D1 in the quantum case. Works perfectly and that works for any dimension. But in n equal 2, well, E2 is stationary, D1 does everything about the K theory. So we can, for N2 from spectral sequence, which is E2, we can read off K theory. That's good luck.
Could you please write the name? This is, yeah, in capital.
STA.
So shit.
Capital letter?
Okay. Yeah, then there's a. It confuses me that it becomes all.
Well, I cannot read your mind.
No, it's really a problem for me. Sure.
Yeah, I know.
Head.
Thank you. Thank you.
You probably know. He has a series of papers about topological methods for the sheets. And it's all there. So we just need what the spectral sequence is there. It's very natural to study this spectral sequence, and it's always the same problem with spectral sequence. How can I get ranked on the higher differentials?
Okay, but do you allow torsion in your K groups?
That's the problem. Well, the spectral sequence has permitted. We start with the real projective space, even the quantum version. We cannot recover the K theory. You only know the K theory of the created object. But even that would be nice to compare. Yeah, and this is a question which I don't know if this identification of generators. So what does it mean? Something becomes trivial. So it has something to do with something on the boundary can be extended to the interior. So you have some these construction, like in the quantum disk, function on the boundary can be extended to the interior of the quantum disk. We will see soon. So the existence of the extension should allow us to compare at least the spectral sequence. So if we could show both have the same spectral sequences, that would be nice. Then we cannot compute, we get only the K groups of the created object, but it's the result.
I have a question about these spheres, boundary spheres of the disks.
Yeah.
Do you assume a relationship between K theories of the ball and the sphere, as we know from the classical topology?
At the moment, I only so the ball should be constructible. So K theory is no. That's we don't assume it, but K theory is clear. So the ball. Well, we look at this one.
I'm asking about the short exact sequence.
Yeah, exactly.
K theories of disk and its boundaries.
Exactly. We would have something like C0 of the disk. Just bigger as a symbol. We would have the closed disk. And then we would have the quotient. We denote, actually, we need only to define C. So C ideal is this algebra. Then the quotient we call the boundary sphere. So any dimension. Zero. And now, this, if I write now that a 6 dimensional sequence should be exactly the same sequence. And in some cases, like the Douglas operators, we even have explicit expressions, which also make me very optimistic. So we can, for the quantum disk, we can write down hot projections, which look like very much like the classical. And this one, all these observations make me optimistic that it might be possible. So if not, so everybody's invited. We just we came to the spectral sequence. We know T1, we know T2 is trivial, and T3 there is some. We know well the serial spectral sequence tells us that the T3 exists, but an explicit formula we don't have. That's our problem. So the star algebras. How much about the star algebras would I present?
So can I have some quick questions before?
Yeah, should I go back?
Yeah,
We have a back arrow.
You can go back. No, back.
so this C-star algebras will be some concrete C-star algebras from graph algebras. Graph C-star algebras.
But I will show you one example, which is we take well here in 2 dimension. I never heard that someone has a non-commutative 1 dimensional interval. So 0 points intervals are classical, and then I start with the doublets algebra. Doublets algebra is a quantum disk and there's a classical boundary, so I can clue on 1 skeletons. Now it's examples we studied. We took this for the higher disk. We took copies of doublets algebras. These are the even dimensional disk. And if I want to have odd dimensional disk, I take a tensor product with the functions on a closed interval. These are our disks. So the interior are the compacts and the CCO functions on the open interval. So we can take the quotient. This quotient is our boundary. And this is just doublets, tensor product of doublets, we could reconstruct the graph description for Szymanski-Horn.
Do you use the generality of the spectral sequence because of low dimension?
Yeah. Yeah, well, that's, I should say, did I finite? I should put finite in the moment. Well, that's enough for us. We start finite, so the spectral sequences will converge after we get stationary. So
okay, so the point here is just you find some C-star algebras, which a family of C-star algebras that sort of reproduce these algebraic K groups, which sort of compatible with all this diagram, like in the commutative case. That's the
so
that's the goal, right? So it's so.
I can go a bit ahead. So we take, for example, we take the doublets algebras as disks, and then we can actively we can construct the complex projective spaces. And then we can solve everything. Now, if it doesn't matter what is this disk. So if you have an idea how to construct complex projective spaces out of disks. So that means that these maps should be the same as in the classical case.
Yeah, but okay.
And then we get E1. E1 has a very nice structure. It's a sort of a chessboard. So whenever you have a spectral sequence of chessboard, but like a chessboard, so that's stationary. That's it. So you can read off the case here. You know each time that you take whatever you call a non-commutative ball with a non-commutative boundary, such that this gives the right 6 exact sequence. You always get the same case theory as classical complex projective spaces. This we can prove already,
Okay.
but that's because E2 stationary.
My point here is that, so even you don't even care about the C star algebra, so you only care about the K theory, like it's just.
Only about K theory, that's right.
So you-
Only about this exact sequence, and then it's 6-time exact sequence in K theory, should be the same.
So this means that this computation of K theory depends somehow only combinatorially on the data related to these boundary maps or these gluing maps.
Exactly.
Yeah, so this.
It's only about when you map the gluing map takes your n-1 skeleton, or the gluing map says how to write this.
Yeah, so your non-trivial zone is the tautological in a sense.
Excuse me?
So I think so.
Yeah, it's like a.
Tautological because you have some combinatorial gadget completing this K theory, and you say that you are comparing things which have the same combinatorial way of computing K theory.
Yeah.
But it's like you see in the bottom line, we know everything, right? In the commutative case, sort of.
Yeah.
So in the upliner, so what's the only thing new probably is but you know, because of this isomorphism at the K theory level, they are the same as the bottom, right? So.
Yeah.
So
This one.
Yeah, the new.
The thing is now you're close to something. Well, let's suppose we know x and -2, and then we glue to a higher dimension x-1.
What do you mean by you know X and minus? You construct a C algebra, that's a.
We know it for n equal to, we know everything. So now prove that if you have, you have a two skeleton, you know that's the right K theory, you can identify K generators. Now look for a map that close three spheres, 3 balls with a boundary on the two skeleton.
So, okay, you know, means that we construct a concrete C star algebras.
Yeah.
So that we have, and then you said you cannot construct maps between C star algebras, but you can construct.
No.
But you do have concrete C star algebras.
Yes.
That's.
Yeah.
Okay,
All constructed by pullbacks.
okay, and those boundary, like, they're all C star.
Yeah.
Okay,
So you are
Everything is T-star.
same question Adam asked.
uh-huh.
But it is, my view is that it's halfway. Because you are not interested only in K groups, you are interested K groups equipped with a system of generators, and you are constructing some purely algebraic maps between their images in K theory.
Yeah.
More than abstract abelian groups, but still not coming from star homomorphism. Yeah, algebras, of course.
Yeah.
Yes, but somehow we keep track on all of these combinatories. Yes.
Yeah.
The same,
Yeah.
the upper part and in the lower part.
But it's a combinatories of gluing
Gluing. Yeah.
theory from Meyer-Vietoris coming from the filtration.
Yeah, exactly. Yeah, you can, well, Meyer-Vietoris can be used, 606 frequencies, quantum maps look very much like Meyer-Vietoris. That was another hope that maybe if I see this Meyer-Vietoris, this construction to compare it with classical case. But if I look at the projective spaces where we have torsion, that looks not so nice, to be honest. It's not so obvious. Why should this element which I construct from Meyer-Vietoris, which torsion it has, why should it be squared 0? It's not so obvious.
So also this isomorphism, does it include this ring structure?
No, it's all no commutative.
Okay, there's no ring structure. Okay, yes, no ring structure.
And we have non-commutative algebras.
Of course, we will see how you realize this slightly vague idea, but I see some problem in this. Because if you think about generators, if you have this filtration, then only the last one can be pinned down as
Yeah.
coming from geometry. Because all the previous ones, if you do it inductively, they are uncontrolled liftings
Exactly.
of previous ones.
This lifting is the problem.
Okay.
That's true. But now it's lifting it always.
So the deeper and deeper the codimension of your skeleton, then generators in the skeleton going to the top
Exactly.
become more and more how to say, you forget about them more and more.
Yeah. And that's exactly the problem which we wanted to solve. Can we lift them in some way that we can compare the lifting with the classical case? It's lifting inside. You have something. So if you have a generator on a skeleton of low dimension, so it can map to something higher dimension. So you have to extend. These six-dimensional sequences, if something in the kernel, then it's in the image from the previous map, so we know it exists, but we cannot get our hands on it and say, well, we can construct them in such a way. That's our problem. So maybe what maybe you have experience. And maybe we are not anymore so optimistic. Maybe it doesn't work just because of these abstract things. So lost a lot of time. Maybe I don't talk about society.
Okay, Kim, maybe just one short question. So, I mean, if from this point of view, because this homology or like cohomology, the non-commutative counterpart will be sort of a cyclic homology or cohomology. So and instead of the K group, it's sort of then it's really more far away, right, from this consideration.
Yeah, well, if you have to want to have cyclic homology, you would take Chern character and map it in cyclic homology.
But cyclic homology needs some smooth structure.
Cycling it requires
More topological.
Okay, C star. Okay.
Second,
Okay.
you have Chern character relating these two. So
Okay. Okay.
it's better to keep to the
Okay.
theory.
Yeah, definitely.
Okay.
That's the best. That's something one you can consider
Okay.
easy.
And on the level of periodic cyclic homology, you are forgetting torsion. So this is much better level of
Yeah.
variance.
Thanks. Good to know. I think so. So yeah. What do I do with these style shapers now? I mean, it's supposed to be lecture for students. Everybody needs style shapers.
Okay, so is anybody in need of a definition of a algebra?
No.
No.
You know that commutative style shapers has more.
I suppose even students present.
Yeah.
They are experts.
Okay, so
If then I show you my famous doublets algebra and I constructed so with doublets operators deforming continuous functions onto this. I want to show you why I call it doublets operator deformation of this. I use a different definition so that we clearly see how do we define functions. So let's talk about the doublets algebra. For you provide it like this, I guess. But that's a Cartesian algebra, but it does not give it. So if you look at the Cartesian algebra, why is it one in this?
Okay, so this will be from the classical context, like
This
No.
what the same as
Not
the.
classic.
I mean,
that's a and I would like to say that's a twofold.
okay, so Topli's algebra, like I think it's just consists of Topli's operators, like it.
Yeah, and this I want to define. Everybody knows what a doublets operator is.
it's good to recall.
Okay, yeah, sure, it's good to recall. I'm just.
I was just waiting for someone that okay.
I just.
So now,
I'm sure it's the.
first thing is,
Yes.
we start with a. That's why I like this. This is my close this in the complex numbers. So complex numbers of modulus less or equal to 1. Then we have, of course, L2 with respect to the Lebesgue measure. With respect to Lebesgue measure. It takes analytic functions A of D fine as so F let's say D C analytic and analytic functions and L2 in the kernel. So yeah, analytic and L2. So this is a subspace in L2. These are called so-called Bergman space. Yes, you can treat some mean value theory that this is closed. L2 closed. So what you need is some mean value theorem, and then you have uniform convergence on compacts, and that guarantees that the limit is again analytic mean value theory. So, okay, since it's closed, we have an orthogonal projection, the so-called Bergman projection, from L2 onto our closed subspace. So, Bergman projection is very well known. Bergman projection. And now we define doublet operators. So for all continuous functions on the closed disk. Continuous functions. In functions of closed disk, we define, and for all, we define it on all elements of the Bergman space. So PF acting on some psi is given by, you multiply with the continuous function. This is definitely not analytic anymore, but then we project into the analytic functions. This is a Wagner projection. So this doublet types are very well studied. There are volumes of books.
I have a question.
Yeah.
I'm more familiar with this construction which uses Hardy spaces.
Yes.
For Bergman, so.
That is like only taking the circle, and it looks very one-dimensional. So I would like to have, I want to tell you, motivate that we deform the functions on a process.
Okay, so
The same thing.
if you, the same thing.
Yeah, it gives you the same topology, but we will see it on the symbol map. Not different, actually, and you will see it on the different. Well, we will see it because if you take here zero on the open disk, see zero functions, these are all compact. So the only thing that matters is the boundary values. And the boundary values, that's what you can do in the Hardy space case. You just care about the boundary values. It has more motivation, you might call it a disk. So, okay. So that's bounded.
So this is just a convenient choice in order to keep close to this idea that we should somehow think of it like a non-commutative quantum disk.
Exactly.
Two-dimensional disk, and Hardy space is more like a circle, not.
Yes, and so that's a disk, you have a boundary circle, and the boundary circle is commutative, and you can do it on one skeleton. So I like this picture a bit more. So
you can think about these operators as functions with a strange multiplication.
well, the multiplication is now.
Because it's multiplication by real function, by this only function.
Okay, I know what I mean. That's a good idea. Yeah, you say you take this algebra and you have a strange function. I think you cannot do it.
I mean,
If you try composing them, you will see the difference.
for sure.
Not usual multiplication. of
Exactly. Yeah, you cannot have df and dg is not a multiplication of something.
F is like the simple
Doesn't work.
operator, right? But it's not unique, right? Could we have like a different Fs, like with a,
Yeah, you cannot. I don't know. You would like to have something like.
No, it's too much.
Yeah, exactly. So.
Yeah, so if you have, sorry, I'm more familiar with the Hardy space picture, but if you have two functions on the disk,
Yeah.
continuous functions that agree on the boundary,
Yeah,
you'll get different tuples operators.
yeah, different. Yeah, and they differ by compact operator.
are differ by compact?
So there must be some formula between the TFTG and TFG are different by compact. Is that right?
No,
We can make it much more explicit,
And it's
but
so yes,
you will
what's,
see it if you know it. I can, well, anyway, I would like to talk about generators, and then you can see the generators. It relates very much to the same generator at the Hardy space.
So what's the kernel of this map? Like you have a function C of D, right? Mapping to the bounded operator on AD. So the kernel is what's the kernel of this map? Like F maps to TF. Right?
should be C0D.
What's the kernel of this map?
Kernel should be 0.
If you model out by compact operators, you obtain everything on the boundary.
There shouldn't be C0D in the kernel.
No.
No,
Okay, you don't have to answer.
you have,
Carry on.
that's a trick. There's a trick. If well, it's a scalar product. I will give you on a basis. When you put it in a basis, you have Lebesgue integral. And then you can look if these Lebesgue integrals are, can you see that's non-zero? So this Z, our basis given by polynomials in Zn, I will do it. So then you can, if you write scalar products, so if function is 0, if all the scalar products are 0, then you see, well, that these zetas and z powers of zetas generate all functions. So it must be L2 0, but since it's continuous, it has to be 0. It's really, it has no kernel.
So in other words, at the end of the day, we would obtain short exact sequence.
Yes.
Okay, that's
Starting
our
compact, yes, then tablets, and then continuous function on what? On boundary?
boundary.
On boundary.
So this is actually which are.
So really, TF is like F, and they generate this algebra.
Okay, sit up.
And this becomes the classical multiplication only after restrictions of the boundary.
So, okay. So let's define now the doublets algebra. It's the C-star algebra. So I call it things which are generated. This C-star. So this means I have a set of generators, a set of operators, and the smallest C-star algebra that contains these operators. So actually, it's enough to take these F in CD, but it doesn't hurt to take all the compacts. So compacts, in this case, I would have to put Hilbert space, so you know what I mean.
So this is what you probably.
So I don't need it. Actually, it's enough here. It's enough to take here the functions which vanish on the boundary. This already generate also compact, but doesn't matter. I just want to say I take it. The compacts are inside. Now it's obvious. So it's a very concrete C-star algebra. In A, D, maybe it's sure. So, okay,
Very short question.
yeah,
In this hard space case, you can also take all possible compact operator and then just take one multiplication by z
yeah,
by isometry. Yes.
yeah.
One isometry. How about this case?
You can check it. So I think now we have a lot of questions about how does it relate. Let's do it. So we take Bergman space. So in L2, these are holomorphic functions. And you know that any analytic function is a Bauer series. So that is these are good candidates for orthonormal basis. Now, then we get the integral. We can have double integral 0, 1 radius, 0, let's say delta, or yeah, well, you will know that it's
Why not to pi?
exactly. Anyway, you can raise it. It's pi. Yeah, you can just take it. Yeah. Okay. Thanks to pi. Now this is EI. And I'm not taking this theta. Let's take something which is. So here we have n minus n, and the parameter phi. Maybe this one's better to see. Here we get r. So we have m plus 1, the m plus n plus 1. T. Well, you can't see. Sorry, that doesn't look nice. So m plus n and 1 comes from the polar coordinates 1. D phi dr.
Maybe dr.
And here you see periodic functions. So that gives us a delta and m. So we have orthogonal vectors, and then the norm is the integral of this power, so polynomials. You get so n is equal to b, n is equal to bn. We can write it like 2 n plus 1. So this plus looks bad, but okay. Let's leave it like this. So we have an orthonormal basis if we define E n to be square root 2 n plus 1 Zn. And 0, you see, well, taking serious, you get all Bauer series. And now we have a look at our Döpfner operator. So Z, well, Z is a function, it's an identity function. Z. E n is given by square root 2 n plus 1. So gets 1 power higher, n plus 1, we multiply by 1. You don't need to project because it's already holomorphic. So now we have to normalize our element again, so we get something like n plus 1 plus 2 e n plus 1. This is the shift operator. It's not the shift operator on the Hardy space. Look a little bit different. But now what we can see is, so we shift operator is just shifting one index. So let's take the difference. So S minus D Z the end is given by 1 minus square root n plus 1 n plus 2 e 1 plus 1. And what you see here, that's not. So this is the modulus of the operator. And then goes to 0 if n goes to infinity. So the modulus of the operator is compact. Then the operator, this space is compact. So we have S is Tn Tz plus some compact operator. Then K. So let me K is short notation of the compact operators on this Bachmann space. Now you know the shift operator on the Hardy space is the Tz on the Hardy space is the shift operator. The shift operator generates the Döblitz algebra and has all compacts inside. This is why is that a generator? Well, that's another thing. I will tell you now that Tz is the generator of my Döblitz algebra in the next slide. So we have the same generators and so we have the same algebra. So why is Tz
Wait, Elmar, sorry, just a trivial remark. But I think that if you look here and you have n equal to m,
yeah.
then if you integrate d phi from 0 to 2 pi, you still have 2 pi over it. But I think it's better to have it from 0 to 1 and put 2 pi in here.
Yeah, but then I get it as well. I will always get a 2 pi.
It wasn't your fault, it was his fault.
Pi. Oh, that's nice. At least this. No, these things. I will make a lot of these.
That's 21.
The fault is a dominant convention.
No, I will. Yeah, I can change here. I should change the normalized.
Yes, be consistent. That's all.
Pi. Okay. No, it's better because I also get rid of this too.
Yeah.
I was wondering why.
I'm happy, yes.
Then. Hi. Thanks. This is okay. Now, I claim that these are things which I really want to use to classify my quantum surfaces. So let's find an argument that d zeta star, let's take it this one, we can take, and the compacts generate my Döblitz algebra. And if these are generators, the shift operator and generator, and then you have the same, really an isomorphism of these algebras. The first thing is we can have a look at the adjoint df adjoint C phi analytic functions. So that's given by C. I can take the Bergman projection here multiplied by F. So projecting on something which is in the image of the Bergman projection doesn't hurt. Now we know that's an L2. This is L2. This. So these are functions. So we know the adjoint of the multiplication operator. We take the first.
You want one file instead of psi, yes? So
That's as I told you, these kind of mistakes. I'm so much concentrating on how to write, I will make a lot of mistakes of that kind. So this is an orthogonal projection that on psi gives the same result. Then we have psi f, but now this is not in the Bergman space, so we have to project phi, and this gives Doppels operator with complex conjugate. Phi. Okay. Now, what we also know is the norm, operator norm of TF is the operator norm of a projection. Well, let me try this one as a multiplication operator. I don't know, maybe you should do something about it, but anyway, I use it in this formula. So this operator norm is a multiplication operator. Well, that's projection as norm 1. It's non-trivial. So we get here the operator norm of F, and that's, you can check, it's the infinity norm. So the infinity norm is stronger than these Doppels operators if you look at it as a linear space. And of course, we know that Sturm-Weierstrass or again, write it in German. So CD, remember what I call Stahlschiefer generated. Z star 1. So which says that we can any f we can approximate by polynomials. And so C sets can be approximated by polynomials in Z and Z star. And so we get DF is so any DF is in the Stahlschiefer generated by PZ, it's adjoint and 1. If you want, you can always put compacts. So these elements generate our Stahlschiefer, and that's okay. Yeah.
So
that's one of the.
So basically, we don't need compact. So you said compacts from like if F vanishing from on the boundary, then you get you map to a compact.
You get compacts, and then you have to only just show that these algebra has only one closed. Well, there's more ideals, but the Jacobson ideal is a compact. It's generated so compacts.
Sorry, Elmar, just a dummy question. Could you explain to me one more time this equality? How do you get with this BDF, BD5?
This part?
Yeah.
Is exactly the definition of TF. And if I project something which is in the image, this is psi again.
Phi.
This is
okay.
vector.
Okay.
so phi and psi are analytic, but not to.
It's not analytic. So these projections don't care. I wrote it in both projections. Of course, I don't need it. Just to tell you, okay, first one I take on the other side doesn't change psi. Then I take SL2 product, F, the multiplication operator with a complex conjugate, and then I take this projection.
So maybe this term should be written in as a first term, then you go to the right-hand side, and finally, from this equality, you can conclude that TF bar is the same as TF star.
And don't you need some parentheses here?
No, these are, well, these,
Excellent.
I do something, I identify a function with this multiplication operator. I didn't want to put here, usually one puts notation multiplication operator, something like, so MF.
But you put parentheses here, so is there a difference or not?
No.
That's what confuses me.
Okay, I'm sorry.
This term bar is an operator. On F bar as a function, but
If you multiply the function, okay.
Now in element, in viewed as an element in L2. The problem is really I should have this notation. I could have definitely so a different symbol for the multiplication operator. Maybe we call it F hat.
Like Jesus.
So now then I can say here it's an operator. And then I'm in L2 and this is multiplication.
Okay. Thanks.
So we know generally. So it's what we see is the first thing which here appears for my compact quantum surfaces. We have an essentially normal operator and we would like to know its spectrum. So we have generator, okay. We know the compacts are inside. Now we did compute, we had D, Z, En or something like square root.
N+1.
This is N, maybe that looks better. 2 En+1. So it's adjoint. We know that adjoint is just taking the complex conjugate. The idea they quantize with analytic functions in physics, it has a much better application if you take a Bachmann space on the complex plane with a Gaussian measure, and you get a representation of the Weil algebra of the quantum harmonic oscillator. The idea is the same, but here we can Bachmann. Yeah,
the same bar.
no, this is Bergmann space, and with Gaussian measure is Bachmann space.
I heard you say Batman anyway.
Okay, yeah, what is this? Different direction and N+1 square root N-1. So we can check the commutator.
Bachmann space. That's a super space.
En. So that gives something. Okay, so first that N, that's the square of this N+1 minus N+1 divided by N+2 and no shift. Again, this goes to 0 or N to infinity. So that tells us that the commutator is compact. Of course, dz commutes with dz and dz star with dz, that's no problem. Now, these are the generators. They are always in the compact. We get df by approximation of continuous functions. But still, any of these commutators are compacts, so we can conclude that this happens, yeah. G is compact. All commutators are compact. Add G in C of D. So it's a slight deformation. It's non-commutative only because of the compacts. But it's non-commutative algebra. E, it's closed.
Okay, and if we also take a look on this sequence, it turns out that this commutator of TZ and TZ bar would be trace class. Am I right?
Yeah, looks like n squared. Yeah, probably.
Something like 1/n.
Probably the n squared get here killed.
Is it somehow relevant to
No, I don't need it.
Okay.
Yeah, but you're right. Yes.
So, okay, we know that's compacts. We know the compacts are insides. Now we look at we can talk about. We know that, so we have the compacts inside. So we get this is a closed ideal. So we can look at the C star extension. Which you know, and which you would like to, here you want to see the symbol map for the Hardy space. So I write the symbol map sigma as a quotient. So the question is, okay, different color. This one, what is it? It is. Right. Okay, to look at it, we can look at the generator. We know that the doublets, our doublets, I remember, is the Sistalchi path generated by Z, DZ, bar 1, and compacts. And you see, really, it's compacts don't hurt because you're all in the kernel. So our quotient is a Sistalchi path because you can all purposes operator we can generate with Z and Z bar. It's a Sistalchi path generated by sigma now. That's sigma. The sigma of its epsilon, and we take 1. So we would like to know what algebra generate these operators. We have a look at. Okay, then we look at its combination D Z star minus 1 on our favorite basis gives something like this was n plus 1 minus 1 n, again this goes to 0. So this is a compact operator. This means that D Z star minus 1 is compact. So we know again, and we know that DZ star is compact. So the image will be commutative. Then you have D Z. This is a star homomorphism. sigma dz. It's, you can take the star out, it's 1, because just it was by contacts, and then again, it's commutative, we know that's commutative, so we have a unitary operator. So the question is, now is the commutative operator generates algebra? Now, okay, so we have the commutative algebra D compacts is the C-star algebra. Generated by a normal operator in some C-star algebra. I need to put the sigmas. Sigma. One, commutative algebra, and we know from a C-star algebra, which is generated by a normal operator, it's isomorphic to continuous function on the spectrum of this operator. So that's what we get.
Sigma, yes.
Yeah, very important. So the question is what is the spectrum? So this is unitary. Here you see the you have unitary operator. No, spectral theorem, so I suppose the algebra theory is known. Now the spectrum necessarily spectrum of dz is necessarily in CS1.
No, that's one.
Yeah, thanks. No, it's eraser.
A symbol. Okay.
Yeah, I know. Sorry.
A symbol of TZ, right? Or TZ.
That was, excuse me, that again, I should start to
Sorry,
give it
sorry,
a-
Elmar.
There's
It's
a comment.
essential spectrum, not spectrum. Essential spectrum of TZ,
Yeah, ASO is essential, or I put the sigma and then I have the spectrum.
or spectrum of sigma of TZ, right? Yeah.
Now it's a sigma. Okay, bit more. So, I'm interested. This is called the essential spectrum, but I'm interested really. I want to know this algebra. D over triplets over compacts. So here I have the operator sigma, which is a commutative. So this is the normal operator unitary, and this unitary has a spectrum in S1.
Sorry, we are not allowed to speak about essential spectrum of sigma.
We are allowed.
Yeah, it's an element, yes.
TZ has an essential spectrum, and what is the essential spectrum? Is modulo compacts, which is the spectrum of this operator.
Now it's okay.
These things, I don't think I get. I will have problems with getting to my plan, but maybe since we discuss these things, my compact quantum surfaces, I will use Count-Douglas-Filmer theory. So I want to describe them by an essentially normal operator. And these are classified, and then I can say we have a classification of quantum surfaces. So the spectral sequence maybe will be very, very short. I don't know if I can have the time. So the question is, we know that closed subset, closed non-zero subset of S1, but is it all of it?
Yeah, that's a question.
And here I actually would need some case theory. Now, so clean. I guess I will use, if I only stick with quantum surface, I will use case theory without having giving an introduction. So the claim is that the spectrum, let me write it, sigma, the central spectrum, is
You could abbreviate this as
what? I didn't want to use sigma.
how do we abbreviate spectrum? How do you pronounce this?
Spectrum.
Oh,
Spec of, so it's okay.
but in German.
Spectrum.
So the abbreviation is spec.
Yeah. Now, well, the spectrum would have a K here. Yeah, that's whenever words are similar to some German words, my pronunciation is horrible. So suppose not. Suppose lambda 0 is an element in S1, but not in spec of the sigma set. And the thing what happens now, I have a circle, I have a lambda 0. So spectrum is compact. I can define a log here. On this place, I can define the logarithm. So I can take, so I can write. So D, this is logarithm D set sigma as some operator I A self-adjoint, and A would be defined 1 over I, ln, which is a continuous function on the spectrum. And then the what I would here should but sigma D set. So if one element is missing, I can apply a logarithm and I get A. Now, since A is a self-adjoint operator, we have our sigma.
But it's unbounded.
Oh, it's bounded.
A is bounded. Because it's fractional calculus.
This is bounded operator. I take the logarithm. It gives logarithm is defined and gives a. Isn't the logarithm as a function on the circle is a bounded?
Yeah. Sorry.
Just have to take the lambda out. Now, so sigma was a map from doublets projected to its quotient. And self-adjoint operators live to self-adjoint operators. So there existed E such that. So
Regarding this question by Piotr, I think that the problem is if the spectrum is whole of the circle, then this mapping maps circle into the whole grid line, and then you get unbounded, something unbounded. But precisely you.
No, I'm
not the
I'm not taking Euclid transformation. The problem is I cannot get continuous functions. I have a continuous function calculus.
Yes. But what I'm saying is that in case if your spectrum is not the whole circle, you exactly precisely for this reason you get that A is bounded.
That's another way. Yeah.
I think if
That's
you would get a bounded operator, but it would be a discontinuous function of your sigma. Like you have to use a bounded Borel logarithm.
I'm thinking about this Stone theorem, stone representation theorem, where you have
Yeah.
correspondence between unitaries on the one hand side and self-adjoint unbounded.
No, it's unitary groups, right?
Yeah, you have to
Yes, okay, it's a group.
strongly unitary groups.
I think that's much deeper.
Okay, okay.
Yeah, I wonder if I take, for example, take a self-adjoint operator which has 0, 1 some spectrums, 2, 3. Yeah, which has gaps, it's unbounded, and then
Yeah.
that gives us the spectrum.
There is no T para one parameter.
No.
There is no T.
But yeah, if so, the self-adjoint operator is a self-adjoint lift. So I find a sigma E is A. So I get, just taking an exponential function, sigma A E B. That would be my sigma dz. And dz is something like shift plus some compact. Now, the contradiction is this is a unitary operator. So index, here it would, this is needs already K theory, but you know what I mean? So the index of an unitary operator, kernel and co-kernel are 0, is 0. But here I have the index of the Z. Well, here you can then put a T, so you have a homotopy to S index S, and that's -1. So if I put here, it's different, so that's a contradiction. We cannot miss any point. So since we cannot miss any point, now our spectrum is S1. This is one generator. So if we so if you define U sigma dz is a unitary generator of the circle. So it's a C** generated by, now I don't have the one is the S1. And what you also know is the winding number. Well, I can prove it with if I take the K theory and the sequence. So that's the index. dz was the index of the shift operator -1. And usually we can take it -1. And we can take, usually you can the part of the generator with winding number, with a positive winding number. And this relates, now we can, this relates the winding number of functions to the index of phantom operators. So maybe as a remark, since we work on the Doppler algebra, it works very well. So what is a Fredholm operator? Everybody knows what a Fredholm operator is? So F, let me make a bit clearer. So is Fredholm means the kernel is the dimension of the kernel is finite. and it's a dimension of the co-kernel. Well, range, let's say, usually we can prove it, but range F range F closed, and so the dimension of the co-kernel.
Your operator is called F, yes?
Yeah, up here,
Euro T.
F like that one is finite. And now I'm comparing the support.
But if the co-kernel is finite dimensional, then the range must be closed.
Yeah, I know.
Automatic, yeah.
Define co-kernel is, it's good to know that this range is closed. One can prove it. Yeah, it's just to skip proofs. Now, this tells us that F from kernel F complement to its range and now it's important that it's closed. This is isomorphic. It's a bijection, so the inverse is bounded. So we have there exists a G in the H such that so GF is identity on, or it's a projection actually. I could say projection. Well, identity on. Let's say projection. So it's a projection on kernel F orthogonal, and FG is another projection. We invert it, and then we have the projection on co-kernel. No, let's say kernel of G or kernel. It's actually, yes, you can say it's the kernel of F star, actually. And these are finite dimensional. Now, if we take the quotient, so G mod compacts, or F, we're talking about our F mod is compact is invertible. And then the index is the only abstraction to have homotopy between operators. So what's interesting is, since we have the quotient in the Kalkin algebra, so the Kalkin algebra is defined by the bounded operators over the compacts. And we know these elements that are invertible in the Kalkin algebra are Fredholm operators. And they are classified by homotopy by the index. And as we have seen, so our generator Z has index -1. So it's a minus the unitary generator of S1. And then we know, well, we can, the indices, all the other operators can be classified. So we have S to the power n has index -n, and S star to the power n has index plus. So these are, well, there's actually a group zeta, isomorphic to zeta, which are characterized by the index modulo homotopy. So these are things which I would like to know, to use for my later on, for my quantum surfaces. So after, let's call it a remark, after a lot of discussion or motivation. So here, sigma ds in compacts, which is isomorphic to CS1, is invertible. So then the index, so it's factorial index of sigma, actually, yeah, the index of the F is minus winding number of the function F restricted to the boundary. That's what I need to do. I haven't told you why. Why is this simple method, the restriction of the boundary? Because sigma, we can write our zeta, let's write it R, U. Yeah, we take the generator on the circle and extend it by the radius. And we know that our Z, so sigma, so our dz is, we write it like this, and we know that it maps into U, which is the function zeta restricted to the boundary. And since we know it from the generators, now we can extend it to all functions.
What is RU? Like any RU?
R is a radius. So R is modulus of zeta, of this zeta. U is a generator, so U is the generator of the systology of continuous function in the circle, its identity. This technically separates the points. So Sturm-Weierstrass generates with 1 and its adjoint. And then we have just Z. We can write like Z AIB. And then we write it. This is a bit confusing because then it looks like a point. And now it looks, I use functions. So Z is a function from the disk. I can use polar decomposition. So this is a unity of generator on the circle. And Z is just the function takes from a point in a circle, assigns its radius from 0. The distance from 0. So now we know a lot about our triplets algebra. We know, so what we know about, you have exact sequence of these algebras.
So is it true for in general that the symbol of TF is just F restricted to the circle?
This I tried to prove, so I proved it now. So I looked at the generator. I have seen that the generator, the sigma has spectrum solid circle. So, and it generates, so and I identify this d zeta with identity functions on the circle, which has winding number 1.
But we have not yet proved this previous statement, right? That this in sort of a big baby index theorem.
But this is the index theorem I used. To prove it, I would use K-theory, but we haven't talked about K-theory yet. Yeah, if you look at
No, but there should be some elementary argument, right? I mean, even before this stage.
But
you are showing this symbol is the spectrum is fully S1, then we cannot yet use K theory yet because
I know, well, I don't want to use KT.
yeah, there should be something just elementary arguments in complex analysis. I mean, just right there.
Well, the first thing we can say is, well, the index map has values in set, in a discrete set.
Yeah, yeah.
Now you can say compact perturbations, you can make it homotopy. So this is homotopy invariant.
Yeah,
I think what we can say is the unitary operator and my Z cannot be homotopy invariant. Now is the question. Well, that's interesting. Now is the question, when are two operators homotopy invariant? And we are exactly, so if you don't want K theory, that contact is Fillmore. And that's a huge theory.
yeah.
So there is a way without K theory, if you make, that was the questions, this was exactly the question contact Fillmore asked. You have a essentially non-operator. So we know the essential spectrum. So when when two operators, one operator is a compact perturbation of CSR.
Yeah.
That's and the bound lattice Fillmore theory tells you exactly. It depends on the winding number of these functions. So we have some compact subset, and then you have some poles, and these poles, then you ask, what is the winding number?
Yeah.
What is the index? So that's how the theory of contactless Fillmore started, but it's a huge theory. It's not trivial. So with K theory, it's easier to demonstrate it. But the result, the interesting result for contactless Fillmore is that algebraic topology of your essential spectrum classifies operators which are homotopy equivalent. Oh, that needs a bit more. Also this needs, I don't know any simple argument.
I was just curious, like we have some elementary argument, then I was curious how far we have reached this about this very specific example.
Yeah,
probably it's
maybe it's K theory, but we haven't seen it, and the complete proof is contact Fillmore theory. And I mean, now I can't think. I won't get it in 5 minutes. I may think about it.
Quick remarks. So this Teplitz index theorem, the argument goes like this: that for this one particular generator, index coincide with this winding number, and then we are using the fact that both index and winding numbers are homomorphic.
Exactly.
So I would say that this is somehow incidentally the same, since reason generator and then both sides are homomorphic.
No contact Fillmore, you know why it is, because you have one circle, so the K homology or K1 of the circle is just that. That's why it works. It's just by good luck.
Exactly.
because it's like if it's somehow easier to say if you view index as a map between these two groups, that's one thing. But once you're landing in like a winding number, is more there is a pairing to produce a number, right? That's more
These binding numbers,
subtle than
binding numbers will show up.
yeah.
The binding numbers, that's binding numbers classify essential normal operator. And I will use it. So I want to write my compact quantum surfaces. Now I want to tell you which one are isomorphic, and then I use exactly the binding number. So we got exact sequence, a simple one, which we now can write compacts, doublets, and here we have S1 sigma. We know this must be an S1 0. And while just by notation, So tuplets we feel like deformed. That was my motivation, deformed disk. Now it's non-commutative. This is something like restriction of the function by in the Doppler operators is exactly restriction of the of functions to the boundary. But you obtain it by taking the quotient with the compacts. So we call the compacts. We can look at the open disk functions on the open disk here. So
This is just notation, yes?
that's notation. So I define this by its compacts. I define quantum disk doppelt algebra and here it's okay. The difference is here we have something in the Kalkin algebra, if you remember. But here I can say I'm interested in such kind of algebra extension.
Okay,
This is a very particular construction. It's not like this Q is some parameter which you pass.
that's is a little confusing.
Quantum.
What notation for quantum?
Yeah, that's
But very often we consider
I know.
the formation and then there is a
using this.
really a parameter. It is not.
And we can write it's this one is universal algebra. If you want to see a quantum, algebra of that star with one relation z minus q z star is equal to 1 minus q. Now you have a parameter. And happens quite often that this is the algebras don't depend from the parameter.
So classical case corresponds to Q equal to what, 0, yes? 0.
2 to 1, it's commutative. That's interesting. Yeah, if you put here Q to 1, you have no bounded. You cannot say it's sure. Why should Z? You have a commutative algebra generated by one complex variable. Why should it bounded? And actually, if you it has universal algebra considers only bounded representations. And there's one which is already it's faithful. It's taking this as kind of weighted shifts. That's already faithful. The others you can take here. You see, you can take a unitary operator. It works, which is the boundary, but it don't. Well, since we have the map from the Doppler algebra to the functions, this sigma decreases norm. So our representation as shift is already the universal representation.
If you included the z star z less than or equal to 1, just to make it a bounded relation in all cases, then you could let q equal to 1.
You mind
This are equal to 1 is that this
Z star z so less than or equal to 1. That just means the spectral condition.
yeah.
It's like a contraction.
Yeah.
Well, together with this guy, I need a spectral condition on Z.
Which is implied by the relation.
Not when q equals
Here,
No, because, yeah, but
to non-classical.
exactly.
it's applied, but go one, I have to put.
That spectral condition then remains for people one. So
Okay, I don't need
So
to
it's
base it.
every one, and if you take Q equal to 0, then this condition turns out to be Z star Z equal to 1, and then Z is just isometry, so it is bounded, yes? That's true.
No, yeah, when q is equal to 1, that you need the additional bounded.
So Q equal to 1.
Yes.
Yeah, zero.
You just have to say.
To summarize, you need to somehow know whether your algebraic relation gives some constraints on the norm, yes? And if you put Q equal to 1, you have just condition for being normal, and normal operator can have arbitrary big spectrum, yes? So this won't force your operator to be bound.
Yeah. So, okay, that's nice that we have. Now I can, I think 50 minutes, I can define my quantum surface. And do that's okay, what we can go was not just the next page. So we have Okay. Let's put this style if I can with my compact. Doesn't matter what's here. Let's skip the compacts. Triplets. Sigma. CS1. 0. Now, let's actually we can define any kind of two-dimensional CW complexes, but let's consider because they are nice closed quantum surfaces. So compact without boundary. With no problem is including boundaries, but just because these are classified, so in algebraic geometry, a circle I can draw. It's here. Oh, I can even full circle. No, let's. So it's big circle. And if you want the orientable case, what we do is, when you can take a polygon or a circle, we mark arcs. Here, for instance, A1, A2, A1 minus 1, A2 minus 1, and then it finishes with some A2G minus 1, A2G, A2 minus 1, A2G. This is minus 1, minus 1. And here I have something more. So if you take this circle as is this, and your marks is arcs, and you close this arc, so we can, okay, any of these functions, so these arcs we can parameterize by continuous functions. So it should be consistent with orientation.
What's the exponent of AI?
Plus minus.
Plus minus 1. Not good in drawing classes. So all these, so the thing I want to say, all these arcs we parameterize for consistent with orientation. And then we know that the torus of genus G is given by taking the disk, the quotient of the disk, closed disk, by this. The equivalent solution is given by identifying arcs. So each point is equivalent to itself, and we identify R, T.
Maybe letter P would be more appropriate than
Which one?
because it's a pretzel, it's not a torus.
Pretzel.
Pretzel.
Yeah,
Yeah, I mean B.
pretzel.
Okay.
Pretzel of genus G. Only if G is equal to 1, it is a torus.
I know because
And then it's a
sounds
donut.
like an
And it's a donut.
so pretzel.
Or a generalized donut.
I'm not sure if I can keep this. I could change it now, but that will be out of my mind. So I'm sorry. I know it looks like a dimensional manifold. No? So pretzel,
Only if genus is G, it is called a torus.
yeah. Okay, I can,
Sorry. One.
I can put it down. Then it's not
Yeah,
a,
but the problem is with T, not with G. What's confusing is with T.
yeah, that's because what I will also use,
Always the same G. But
what I also will use is that let's put it down, so it's not an exponent. It's a connected sum of something. So, okay, you want to have PPDs.
Okay, now it's
Left it.
okay, now it's better.
So I agree. Let's put at least, let's put it down.
Yeah.
I will have problems again with this notation. So with index are not powers. And yeah, so here we identify with method inverse arc E for all E in so on.
I'm a bit confused by this X.
Well,
Equivalent to X.
any element is equivalent to itself.
Aha.
I don't know, this one is the equivalence generated, and if I want to have a full equivalence relation, every element is.
Okay, so really meant it, okay.
And here, what matters is on the boundary, yeah, we do arcs, we parameterize, and then it's each point on the arc has its corresponding point and its inverse arc. Well, here, well, that's all written like some sort of normal form, but I actually don't care. So now I can define my definition of my orientable flows wonderful surface. Let A1 and its inverse up to A for G and N. B, its inverse. The arcs on boundary such that taking D, this is equivalence relation above, is homomorphic to oriented closed surface of genus G. Then we define continuous functions on a non-commutative closed oriented surface of the G. The G was bath, so I don't have to fight here too much. But now it's Q, like quantum, is defined as we take Töpfelsabeiras and applies a symbol map. Now the symbol map, now we are talking about functions, and these functions should not separate points that are identified.
belonging to. Not contained, but belonging to.
Where's belong?
In your capital T and element.
Element.
Element of T.
So sigma T is a function on the circle. Now I have I T is the same as sigma D I A minus 1 T. For all I T and so I'm saying that the functions on the boundary, I apply sigma, I function on the boundary, it do not separate this point, and then this is, if it would be commutative, this would be exactly the functions on closed orientable surface of G. Now, time's over, so in the case, so the remark maybe.
So, sorry, do you have to add in the compacts now? Because they aren't.
That's a good. Yeah, while the complex is 0 and satisfy all. All the complex.
Oh, okay, of course.
Rune is only on the boundary.
You're not giving generators, you're giving all the elements.
Exactly.
Sorry, yes, yeah.
So the remark is actually it's a family. Family of these double keepers. Because the only conclusion that I put on this art was that we get a classical surface. So this Orten, normally I can change the Orten, whatever. I only ask for the quotient to be the right classical object. So these are different sub-C algebras. And to prove that we actually define isomorphic C algebra uses this Brown Douglas Filmer theory. Now I will show that I can generate it by one essentially normal operator with the central spectrum will be this wedge product of arcs, and then happens what the classification tells me. I have to check the winding numbers, and then we look at the winding numbers, and then we see, okay, all the winding numbers are the same. These are isomorphic C-algebras. Now, if I define the non-oriented case, we will see differences, and that's why I have no time to do it in one go. There will be, if you take wedge, so it's a non-oriented surfaces, we can take K wedge sums, K connected sums of here projected space, and then another number of tori. This will be a non-orientable closed surface. They are homomorphic, but the C-algebras are not. That's next.
Sorry, but there is no Q on the right-hand side in your definition.
You want the right side?
But Q is just words.
It's only on the left hand.
Q is not a parameter. Q is shortened for.
Q.
That's a symbol for quantum.
Yeah, okay, but where? Okay, but I understood that it depends on Q, no?
No.
That's the point.
Okay, so it's Q for quantum and not for
Yes.
some variable.
Could have depended if you insist that your Teplitz algebra has this particular form with this relation.
But it's still
holding
Q dependent.
Q, but
Still independent.
yes, but
We have to do this algebra anyway, and then it's.
It's one of these nice things that he gave a description in terms of subalgebras of Teplitz algebra. And yes, I mean, you can define the Teplitz algebra as the universal C-star algebra formally depending on Q, but when you prove it doesn't depend on Q. So now here Q has a double role. You can view it as a parameter. It's not the same. I mean, you can look at it like this. If you look at the Teplitz algebra really generated by Q-dependent relation, but you don't have to. You can look at Q as for quantum. Now, because the time is almost up, can you do for me two difficult things?
That's probably, I don't know.
Okay, can you write two things? 6 sigma and T genus 9.
You want to see the difference?
Yeah,
So
6 sigma,
6.
sigma.
Sigma do the same thing the other way, it looks exactly the same.
Okay, so that's 6 sigma. Okay, now this T genus 9.
G.
No, T with genus 9.
Okay. G.
You are cruel.
Sigma is a very big confidence level.
Okay. Okay,
So, yeah,
I made my point.
I should. So it's T sigma 9. I type it like this. That's better.
Okay, so thank you very much for the first installment. This is a good time to stop the recording. Yeah. And we resume. Stop